To extract the raw materials that build our modern world, we dig deep. In open-pit mines like this, operations happen on a scale that makes standard heavy machinery look like children's toys. We are talking about moving literal mountains of solid rock, day in and day out. And doing that requires machines like the Liebherr T284. Fully loaded, this single vehicle weighs over 600 tons, more than a Boeing 747 at takeoff. It hauls 363 tons of earth per trip, rolling on tires as tall as a 2-story house, with each one weighing 5 tons. Stand next to a machine the size of a 3-story building, and you expect the ground-shaking roar of a massive diesel engine. But you won't hear one. Instead, there's an eerie silence. The vehicle emits a high-frequency hum, sounding exactly like a consumer electric car slowly cruising through a parking lot. That sound points to a bizarre engineering reality. From your everyday motorcycle to a giant container truck, nearly every vehicle on Earth moves using interlocking metal gears. But this 600-ton behemoth has absolutely no gearbox. It has no clutch and no drive shaft. In conventional mechanics, engine power travels a long journey. It passes from a clutch, through a gearbox, along a drive shaft, and out to the wheels. At every step, metal grinds against metal. Usually, that friction is manageable, but immense weight acts as a multiplier, turning normal friction into intense physical pressure. If you tried to scale up a traditional clutch to meet this load, the physics of friction would become a destructive force. The energy required to move 363 tons of rock from a standstill would generate enough heat to liquefy the metal clutch plates in seconds, effectively welding the entire drivetrain into a single fused mass before the vehicle could even clear the loading zone. The engineers realized they were facing a hard physical limit. Building a bigger gearbox wouldn't work. The material properties of the metal itself would fail. To move this much weight, they had to completely abandon traditional mechanical linkages. The solution sits inside the chassis. This is a massive V20 diesel engine capable of producing 3,600 horsepower, but it does not turn the wheels. Its only job is to act as a mobile power plant. The engine spins a high-powered alternator directly attached to it. That alternator pumps out an enormous electrical current, which travels through thick, wrist-sized copper cables straight down into hidden induction motors housed inside the 2 rear wheels. Pushing that much raw current straight to the motors would burn the vehicle down. So engineers use high-tech semiconductor components called IGBTs, or insulated gate bipolar transistors. Think of them as high-speed traffic controllers. They switch the massive electrical current on and off thousands of times per second to perfectly regulate the flow. By replacing physical gears with carefully directed electrons, the truck eliminates metal fatigue entirely. The electric motors provide maximum torque from 0 RPM, allowing a 600-ton monster to inch up a steep mine shaft with perfect smoothness. Getting 600 tons up a hill is one physics problem. Safely stopping that same weight as it descends a deep, slippery mine slope is a matter of life or death. Again, traditional mechanics fail. If the driver relied on physical friction brakes, the sheer kinetic energy of the heavy payload pressing the brake pads against the wheels would cause them to burst into flames within seconds. To stop safely, engineers deployed dynamic electromagnetic braking. When the driver lifts off the accelerator going downhill, the electric motors in the wheels instantly switch their operating mode. Instead of consuming power, they become giant generators, using electromagnetic resistance to drastically slow the vehicle's rotation. This generates a massive electrical surge, creating resistance equivalent to 6,000 horsepower, roughly double the output of the truck's own engine. It is a lethal amount of energy. No battery on Earth can absorb and store a current that large, that fast, without detonating. So the engineers route the energy away from the wheels and up to the roof. There, it hits a massive grid of electrical resistors. The current flows through the grid and is converted directly into scorching heat, which giant cooling fans immediately blast into the sky. Instead of relying on brake pads gripping a metal rotor, the truck magnetically transforms millions of pounds of kinetic energy into harmless heat. As it rolls downhill, it acts like a giant mobile oven, safely radiating that heat away. Years ago, designers created this complex system solely to bypass the physical limits of metal friction. Without realizing it, The mining industry had engineered a fully functional, heavy-duty electric vehicle architecture decades before it became a global trend. Because the mechanical drivetrain is entirely missing, the propulsion system is isolated from the power source. The electric motors in the wheels do not care where their electrons come from. High in the Andes at copper mines in Chile, this architecture is already being tapped. When the Liebherr climbs a steep incline, it raises two steel arms on its cabin roof, called pantographs, to touch high-voltage overhead lines. The diesel engine drops to idle, and the truck climbs using grid electricity, cutting fuel consumption on that stretch by 95%. Right now, engineers are testing the removal of the diesel engine from this chassis entirely, replacing it with giant battery packs or hydrogen fuel cells. They don't need to redesign how the truck actually moves. They only need to change the source of the current flowing into the motors. The T284 is evidence that the shift toward electric drivetrains wasn't always a choice of policy, but a requirement of physics. By solving the problem of heat and metal fatigue through electrons, the mining industry built a bridge to a different power source long before the rest of the world hit the same wall.